All right, I think we're going to get started. If you can't hear me, just type a message into the chat. My name is Travis.Nielson. I'm a geophysicist with Olson Engineering, and I'm going to be giving this webinar on seismic refraction for near-surface geophysics. This is going to be a semi-technical presentation, meaning that we'll get into the algorithms, but we're not going to delve in the math. And the intended audience for this presentation are geophysicists that are new, or geophysicists that are, or engineers and geologists that work with geophysicists and want to have a better understanding of what seismic refraction is. If you have any questions, please type them in the chat. We will try to answer them later. And all right, I think we'll get started. All right, so what is seismic refraction? So a seismic refraction survey is a P or S wave survey that uses the travel time of refracted and direct arrivals. Refracted or direct arrivals are those that travel parallel to the surface from the source to receiver. Refracted arrivals are those that travel from the source down along a velocity interface, then back up to the receiver. This is obviously a simplified explanation for what they are, but it's a good conceptual model. So refracted and direct arrivals are always the first to arrive at a receiver from a source. So we oftentimes say refracted and direct arrivals are we'll just call them first arrivals, just lump them together. So what does refracted and direct arrivals look like in data? So here we have a very dense, very nice shot gather. And these lines highlight the various arrivals. So we see this red line, those are the direct arrivals, the ones traveling parallel to the surface. And we have this blue line, these are the refracted arrivals, those that are traveling along a velocity interface in the subsurface. We can also see in this data set, we've got some nice reflected arrivals, and then we've also got a surface wave window. So another way we can visualize refracted arrivals is by taking the lines that we plotted here and then plotting them, essentially just flipping the time axis. So we can see we've got this direct ray line and we've got this refracted ray line. One advantage of plotting it this way is that 1 over the slope of this line is the velocity of the interface or of the medium. So at the top layer, 1 over the slope of the direct ray line is the velocity of the top layer. And for the second layer, 1 over the slope of the first refracted line is the velocity. One key concept is the concept of crossover distance. This is the distance in which the direct ray is no longer the first to arrive at the receiver. So at a certain offset from the source, the refracted rays will become the first to arrive at the receiver. So they'll become the first arrivals. So looking at that previous shot gather, this right here is the crossover distance from the source. So I talked a lot about the concept of rays being refracted or traveling along a velocity interface. That requires a blocky model of the subsurface. So a model in which we have discrete layers, so like disaggregated soil, saprolite, fractured bedrock, discrete layers with discrete velocities and no transition between them. Simply, it steps from one velocity to another. And in these situations, the rays will travel down. They'll either travel along the velocity interface or get bent by the velocity interface and travel along on the lower interface. If we have a smooth velocity gradient, like what we'd expect to see in a weathering zone, then rather than the rays being refracted along the velocity interface, we'll get these curved rays. And we refer to these as diving rays. So our seismic refraction equipment, it's pretty straightforward and pretty similar to what you'd use in just about any other seismic or active source seismic survey. You have geophones, vertical component if you're doing a P wave survey, and horizontal component if you're doing a shear wave survey. You have a seismograph, This right here is a geometric geode, which has 24 channels. And then you need some cable to connect everything together. The other thing that you need is a source. The most common source is a person hitting the ground with a sledgehammer. This is me in Las Vegas. And less common, but certainly more powerful, is an automatic weight drop. That's what we have here. This is an automatic weight drop that we have at Olson Engineering. This hammer weighs 23 kilograms. I can't comfortably swing a 23 kilogram hammer. And this hammer is also being accelerated into the ground by very strong rubber bands. So the advantages of an accelerated weight drop is you can hit the ground a lot harder. You can put a lot more energy into the ground. That being said, they're much less portable. This thing weighs about 250 pounds. So you usually need it mounted to a cart or mounted to a vehicle. For 99% of our surveys that are using seismic refraction as their primary output, we will use just a person with a sledgehammer. So field procedures in seismic refraction, people do it in different ways, but how I like to do it is I first set out a survey tape, then I place the geophone, or then I place the cable out, then I place in the geophones. So this is a time lapse that we did of a survey that we did near our office. Unfortunately, we didn't start the time lapse until after we had everything set up, but if we watch the video, we can see us chatting. And then Ryan, he's swinging the sledgehammer. He's being the source this time. Those of you that have done seismic refraction before might be surprised that we're able to do it so close to pretty major highway. This is I-70. And the reason why we're able to do it next to I-70 is that passenger vehicles like this don't impart a lot of surface waves into the ground. Surface waves are primarily what are going to interfere with a refraction survey. So they don't impart a ton of noise. What does impart a lot of noise are heavier vehicles like semi-trucks. So we time our shots to make sure that we time our shots so that we avoid when semi-trucks pass by. And if we do happen to get some noise from a semi-truck or another vehicle, then we can unstack the data. It's more labor intensive to do it this way, but it does improve our data quality this way quite a bit. So you can see Ryan's going through, continuing to hit the ground. And every location that he hits the ground, we refer to that as a shot point or a shot location. And you can see we're collecting. We are picking up our equipment, and we do this in the reverse procedure that we lay it down, pick up the geophones, roll up the cable, pick up the survey tape. So in that video, we showed what we would call a fixed array survey. That's where we lay out our array and we don't move it. So this is kind of a simplified diagram. So we've got 2 geodes with 6 channels each, a little bit unrealistic, but much easier to draw. And we would hit the ground at the very edge of the array, a couple times within the array, and that would be our survey. If we're in a situation where we need to cover more ground than is possible with our array, then we can do what we call a roll-along procedure, where we set up our 2 geophones, our 2 strings, and then we shoot through one string, and then we move it to the other side, and then we shoot through the other string, and we would just complete this procedure until we reach the end of our survey area. So one rule of thumb that I always use when doing seismic refraction is that the sample depth is 1/5 of the array length. So if I'm looking at a target that is 20 meters down, then I will have a 100-meter array. I don't generally want to go beyond 100 meters because geophone spacing is related to resolution. So I want to balance the my sample depth with my resolution. So everything we've talked about and everything we're going to talk about is pretty much focused on P-wave refraction. It bears mentioning that S-wave refraction is a method that exists, and you can use a lot of the same equipment and processing software to conduct it. The big difference is that you need a horizontal component geophone like this, and you need some sort of shear source. Swinging a sledgehammer against the ground vertically is not going to produce enough shear energy in order to do a shear wave refraction survey. So you need something like this, where you have a cleat that you hit, cleat that you put diagonally in the ground and you hit, or a shear AWD, or you can have something like this, which is a vehicle parked on top of a piece of wood. Shear wave refraction has fallen out of favor as a shear wave survey because MASW is a lot easier to do. MASW doesn't require a shear source, and shear sources just have never been that effective. It's pretty hard to impart good shear motion to the ground. There are still situations where I would want to do a shear wave refraction survey over an MASW survey. And these are mostly areas where you have a lot of topography. MASW assumes a 1D velocity model. So across your array or portion of the array that you're using for processing, you need to have relatively flat ground. That being said, there aren't too many circumstances where I would do an S-wave refraction survey. Okay, so what is seismic refraction used for? It's primarily used for structural characterization. So looking for things like faults, looking at bedrock topography, and looking at fill depth. It's also used for what we call rippability. So this here is the result from the survey which we had that video for. And we did that survey at that location because we knew there was a fault there and we wanted to see if we could image the fault. And what we can see from the results is we have this pretty clear velocity anomaly, which we interpret as the edge of the fault. So this is another example. This is a survey that I did to map the bedrock topography. Refraction surveys are really great for mapping bedrock topography because in certain areas, bedrock can have a lot of topography to it. And there are, and in the weathering zone, weathering always decreases P-wave velocity. So as you go from fresh bedrock to fracture to saprolite to soil, your P-wave velocity is always going to decrease. And at least for granite, there's really strong established relationships between P-wave velocity and weathering degree. So at this survey, this was a catchment in Idaho. For scale, line 2 is about 1 kilometer long as the crow flies. And we're looking up a drainage. So we're sitting at the bottom of the drainage looking up. And because of this established relationship between weathering degree and P-wave velocity, we're able to take the 3.5 kilometer per second contour and say that's the top of fresh bedrock. That's this black line here. Whether fresh bedrock from an academic perspective, which this was for, or is the same thing as fresh bedrock from an engineering perspective, is a little up in the air. So you would need to work with your geophysicists to understand, like, to determine what your parameters for bedrock are. If you're doing a refraction survey for bedrock topography. And the other thing, the example that I'm presenting is for measuring the depth of fill. So this is a site that was an old smelter, and we knew that there was 20, 50 feet of fill on top of a claystone bedrock. And we can see from the results, we have this really homogeneous top layer and then a rapid increase in velocity. By using adjacent boreholes, we're able to determine which velocity likely corresponds to the top of bedrock. That's what we highlighted in this red line. So next thing I want to talk about is rippability. So rippability is a parameter established by Caterpillar, which is how easy something is going to be for for some of their equipment to excavate that material. This is a common result for quarrying because rippable rock is usually what they want to try to quarry. They established a relationship between material and P-wave velocity, and that's what this yellow band is for each one of these materials. And so for granite, you can see the rippable band is between 3,000 feet per second to just below 6,000 feet per second. The nice thing about this is because it's such a established relationship, we can simply take our P-wave velocity profile and group the contours so we can group and see which areas are rippable, too low, marginal, or non-rippable. So next thing I want to talk about are some of the limitations that seismic refraction has. And one of the big things is resolution. This is not so much a limitation as a constraint that you need to be aware of. So at the surface, your resolution is roughly 1/2 your receiver spacing. That changes with depth, obviously. But if your resolution is too low, if your receiver spacing is too large, like we have here, we have only 5 receivers for 3 refractors. You're not necessarily going to image all 3 refractors with confidence. Here we have a good number of receivers versus the number of refractors. And so we can easily see that there's 3 refractors down there. This is somewhat of a simplified view of refraction, but it illustrates the point that don't maximize your array spread length at the sacrifice of your receiver spacing. You need to balance those 2 parameters. So the big limitation of seismic refraction are low velocity layers or velocity inversions. These are situations in which the top layer velocity, or there's a high velocity layer over top a low velocity layer. So V2 has a lower velocity than V1. What'll happen here is when you hit the ground, the ray will travel down, and rather than getting refracted along the velocity interface, it'll dive deeper and will refract along a lower velocity interface. And the result is that you'll have 2 refractors rather than 3, and the velocity for your refractor here is going to be distorted. It's not going to be the V3 velocity. It's going to be some weighted average of the V2 and V3 velocity. This is a situation that you commonly see in arid environments where you have caliche. Caliche is a carbonated soil that is typically very hard and has a very high velocity relative to looser soils. That being said, if you're able to put your array half on your velocity inversion, half off your velocity inversion, you do have a limited ability to image the velocity inversion and to be aware that it's there. That's what this situation is here. So we've got a caliche layer here, and then we're able to put our array halfway on the caliche layer, halfway off the caliche layer. And we can start to, because we have shots halfway off the caliche layer, we can actually image a little bit of that velocity inversion. You're never going to be able to perfectly image the velocity inversion, but you're able to say something about it. We did this survey looking for faults, and initially we interpreted this velocity heterogeneity as a fault. When we revisited the site, we determined that it was likely not a fault. So like I mentioned, we revisited the site, and when we revisited, we collected more and longer lines. So this profile here is in roughly the same location as this profile. And you can see we're able to do quite a few more shots. And for portions of the survey, the array is entirely on the caliche, so above a velocity inversion. And for a portion of the survey, the array is half over the velocity inversion and half off. So when we're completely on the velocity inversion, we're not able to image below the velocity inversion. And when the array is half on and half off, we do have a limited ability to image under the velocity inversion. So at this site, we also did MASW processing. That's what this is here. And that can clearly show this caliche layer here. And one of the reasons why we're not imaging below the, we're not getting any signal or any information below the caliche layer is that as the rays traveled down, they traveled through here, they dipped down and they refract along this interface. But our array was not long enough to actually catch the array as it moved back up. So another limitation of seismic refraction tomography is if your layers are too thin, you might not be able to have a distinct refractor. So that's what this situation is here. So at no point, while we do have refracted rays from this thin layer, this V2 thin layer, at no point are they the first arrival. At no point is it faster for a ray to travel down through here, along here and back up than it is to travel down through here along this faster V3 layer and back up. This is a problem to be aware of. It's not a super common problem, but it's always good to be aware of these limitations and try to incorporate a priori information into your interpretation. So next thing we're going to talk about is refraction processing. Refraction processing has come a long way, especially in the last 15 years. And refraction processing methods can be kind of broken up into two categories. We have non-tomographic methods and tomographic methods. And non-tomographic methods can be broken into classical Snell's laws methods, then a little bit more sophisticated computer-based methods that can also be broken up into categories like layered methods and smooth methods. These non-tomographic computer-based methods tend to be very unstable. And they've since fallen out of favor as a deliverable to a client. And what I mean by unstable is they're very sensitive to any weird data or any unusual user input that you give it, and it can put out very unrealistic results. Tomographic methods have since become the standard in industry. And that being said, like everything, they can be broken down into categories. You have the older, what we call infinite frequency tomographic methods. And then we have things like partial frequency methods or finite frequency methods. And we'll discuss these in a little bit more detail later on. And then kind of the most sophisticated way to process refraction data right now is what we would call full waveform inversion. And while I say that tomographic methods are the industry standard for deliverables, we still use these computer-based methods as initial models for the tomographic methods. Tomographic methods always need an initial guess to get going. And I say that full waveform inversion is the most sophisticated way to process refraction data. It needs a very accurate initial model to refine from. So we'll use infinite frequency or finite or partial frequency methods and initial model for full waveform inversion. So if you're doing full waveform inversion, it's conceivable to use all three classes of methods. So the first step in just about every refraction processing is picking the first arrival. And there's some tricks to this that we're going to go through. So this is an exceptionally clean data set. And I've got my first arrival picks as these red X's. And we're zooming in to a portion of that last figure, and we can see in a little bit more detail where these red X's are. So some people will pick the first motion. So you would pick here. However, the first motion, which is usually in the negative direction, tends to get swamped out by noise. So I tend to prefer to pick the first motion in the positive direction. So I will pick the crossover time between negative and positive, so I'll pick here. One common technique to improve picking in noisy data, so this is a pretty noisy data set. We've got some cultural noise. It looks like we've got some vehicle noise. We've got a pretty strong air wave. So one common way we can improve our ability to pick this data is by applying a bandpass filter. So here I applied a 10 to 80 hertz bandpass filter. And we can see that especially through here, it has improved the clarity of the first arrivals. That being said, you want to apply bandpass filters with consistency and caution. Because refracted wavelets are pretty broad band, any frequency filter that you apply to it is going to distort the wavelet. So to demonstrate that, this is that nice clean data set that I showed you first. And now I've applied a 50 to 100 hertz bandpass filter. So you can see that the zero amplitude crossover time has shifted. So these red X's haven't moved in time, and you can see it shifted several milliseconds. So what you want to do if you need to apply a bandpass filter is to try a couple of different filters and try to find filters that work for the whole data set. You really want to avoid drastic jumps in your bandpass filter frequencies. All right, so now we're going to talk about the non-tomographic refraction processing methods. And first we're going to talk about Snell's law, and then we'll go briefly into the computer-based methods. So the Snell's laws methods, these are using the principles derived from optical physics. I can't say they're used very much outside of as a way to like torture students to make them plot time offset distance plots with shot gather data. I think I did it in grad school and I haven't done it since. So because we're able, when we have a time offset plot like this, we're able to pretty easily derive the layer velocities. What is the missing parameter to create an Earth model is the layer thicknesses. And these equations can be derived from Snell's laws for Z1 and Z2, so layer thickness for 1 and 2. And you can apply this to an arbitrary number of layers, so it's not just limited to a 3-layer model. And so the parameter that you need to pull from your data set is this T1 and T2. So this is the zero offset crossover time. And how you derive that is for your first and second refractor, you plot that line, back project it to your zero crossover axis, or zero offset crossover, and you figure out that time, so T1 and then T2, and then you're able to use these equations to derive it. There are ways to modify these Snell's law methods to handle dipping and to a limited extent undulating refractors, but like I said, this isn't really a method used in industry anymore. So computer-based or other refraction processing methods, these are methods that, while they're not necessarily tomographic, use computer inversion or some type of computer algorithm to produce a result. And these can be loosely categorized into layered methods and smooth methods. The layered methods, like the plus minus and CMP methods, these methods rely on a user input for how many refractors there are, and they're able to produce relatively discrete layered models. So you can see this here. So we've got a pretty homogeneous top layer and then a slightly varying bottom layer. And there's also methods like the delta TV inversion, which uses the relationship between offset velocity and travel time to produce a smooth 2D model of the subsurface. And like I said earlier, we do use these methods still as initial models for tomographic methods. In particular, we use this delta TV method a lot here at Olson Engineering. And what we'll do is we'll take this delta TV 2D model and then we'll create a 1D model from it by averaging the velocities over all offsets at a given distance, so that we're able to produce a smooth 1D model. So now we're going to spend some time talking about tomographic methods and what tomography is, and then we'll get into a little bit more detail about the various algorithms that are categorized as tomographic. So tomography in geophysics and seismic refraction is in principle the same tomography that they use in medicine. So a CT scan is computerized tomography using X-rays. Seismic refraction is almost the same thing using seismic waves. One of the advantages in medicine is you can scan someone and shoot X-rays into them from all sides. Generally, in geophysics, we're restrained to the top. And the processing flow for tomography is always start with an initial model, simulate the survey, and then calculate the data fit or difference between your simulated survey and your real survey. And then you check your convergence. So you'll have some sort of convergence criteria to say whether your model is converged or not. And if it hasn't converged, then you use the difference in data fit from your simulated and actual data to update the model, and then you run through this loop several times until your convergence criteria are met. So this is an initial model. This is a 1D smooth delta TV version, or 1D smooth delta TV model. And this is from the data set that the video is from. So you can see we've got this initial model. It is 1D and adjusted for topography. So the next step is to simulate a survey. This video has nothing to do with any data that we've collected. It's just a nice little animation. Then we calculate the data fit. So what we do is we compare the modeled first arrivals, so that's these blue crosses, with the manually picked first arrivals, that's these X crosses, or red X's. And then from that, we check whether the data has converged. So we have a couple different ways of defining convergence criteria. And these can be like root mean square error. So the root mean square error of the modeled and real data, or iteration count, or you can have things like change in RMS error over iteration. An RMS error can either be an absolute RMS error, or an RMS error in a unit like milliseconds, or it can be a percent. So you can have an RMS error as a percent of, say, the average travel time. For the data set that I'm showing, the RMS error was set to less than 2.5 milliseconds, or 40 iterations. And so this is a plot of RMS error over iterations, again, from the same data set that we had that video from. And you can see the biggest drop in root mean square error is from iterations 1 through 5. After iterations 5, there is still a decrease in root mean square error from iteration to iteration, but past 30, it's pretty flat. And one thing to note is that I set a convergence criteria of 2.5 milliseconds or 40 iterations. Given the slope of this, I don't think it would have ever gotten to 2.5 milliseconds. So it was good that I had that 40 iteration limit. So now we're going to go through and I'm going to show you how the intermediate results look like. So how the results after, so these are the results after 5 iterations. So going from that 1D smooth model to this, we can start to see that we're developing this velocity anomaly right here. And then after 10 iterations, we can see we still have that velocity anomaly. And the velocity of that anomaly is increasing. 15 iterations looks pretty similar to 10 iterations. Again, that velocity anomaly is increasing in velocity. And then after 40 iterations, where we've hit that iteration limit, we can see the velocity here is a lot higher, and we've got some pretty good definition on what that anomaly is. So one key concept in nonlinear geophysical inversion is what we call non-uniqueness. And that's that there are an infinite number of potential Earth models that can fit the data. So a joke that we like to say is in geophysics, it's not 2 + 2 = something, it's something plus something equals 4. And we limit the, so you might ask, like, if we have an infinite number of potential Earth models that can fit the data, how do we come up with a result? And we do this by biasing our algorithms to eliminate a lot of the unrealistic results. So we'll limit lateral velocity changes so that you can't have a black hole in the subsurface or something like that. But even when we do these biasings, you can have situations like I'm showing here, where we have results with similar root mean square error. We would generally say lower root mean square error, more likely to be, or lower root mean square error, the better the model fits the data. So you always want to choose the lowest root mean square error. But in a situation like this is the same data set. I processed it in 2 different ways, and the root mean square errors are very comparable. So I said I processed it in 2 different ways. How did I get these 2 different models? Well, I used 2 different initial models. The data set on the left here is very smooth, you can see, and the data set on the right has this rapid velocity increase down here. So if I use, to generate the smooth final model, if I used a smooth initial model. So this is a delta TV inversion that's been 1D smooth. And you can see it's resulted in a pretty smooth final model. Now here I used a layered model, a layered initial model, the CMP model. And you can see that it resulted in a pretty rapid velocity increase at depth, so more layered velocity structure. So which is right? Given just the information that we have, you can't actually say which one is more likely to be right. But at this site, we had well information, and we knew that we had 15 or so meters of fill over top of claystone bedrock. This looks a lot more like 15 meters of fill over top of claystone bedrock. So this is the model that we presented to our client. The default model, though, for most refraction methods is to assume that we have a smooth earth. And that's because if you assume and you use smooth initial models, you have a much more stable inversion. So this is always our first guess. Whenever we're doing refraction processing, we always try a smooth initial model first, and then we'll try experimenting with a layered initial model. All right, so now that everybody has a little bit of a background on tomography, we're going to get into a little bit of the weeds of different tomographic methods. So like I mentioned earlier, tomographic methods can be broken up into ones where we assume infinite frequency. And what we're doing here is we're assuming that the seismic wave has an infinitely high frequency and thus has an infinitely thin ray. Infinite frequency methods only incorporate first arrival time, and they are computationally cheap and are the older tomographic methods. Now, more recently, we've started developing tomographic methods that take the infinite frequency assumption, but also add in some frequency information. So they're using frequency information in some way, and they still only incorporate the first arrival times. But these are these use a little bit better assumptions. So are assumed to be a little bit more robust and accurate. And then we also have much more recently, frequency-dependent tomography. This is where we're not using any infinite frequency assumptions, and we're fully modeling the frequencies of the waves. But again, we're still only incorporating first arrival time. And lastly, we have full waveform inversion. This uses not just arrival time, but the shape of the wavelets it uses the shape of the wavelets as part of its inversion, and the advantage to that is you have a large increase in resolution. And one misconception is usually when you do full waveform inversions, you're not using the full shot gather. You're usually using a clip portion of the wave field. So if we're doing full waveform inversion for refractions, we'll clip out the refractions, and that will be what we're using for inversion. Currently in commercial software, we really only see infinite frequency and partial frequency methods. Okay, so infinite frequency tomography. So these can again be broken into two categories. We have ray tracing. This is a method in which we use a ray tracing algorithm to find the fastest path from the source to receiver along a series of nodes. So we calculate the ray path, and then we calculate the travel time. The other option is what we call wavefront tracking. These are when we simulate a wavefront, so we know the travel time from source to hypothetical receiver over here. And once we know the travel time, we figure out the ray path. So one of the big downsides of infinite frequency tomography is we're assuming that the rays have infinite frequency and infinitely thin. When we update the model in tomography, we update the model along the ray paths. So if you have a bunch of infinitely thin ray paths, then you have to go from infinitely thin ray paths to a fully realized 2D model. So you have to do some sort of interpolation. Now, partial frequency methods, the one that we're going to describe here is what we call the wave path equal travel time tomography method. Assumes an infinite frequency ray path. So it's so modeling the ray path from receiver to source, assuming infinite frequencies, this red line. But rather than just updating the model along this red line, it's updating a model along a hypothetical Fresnel volume. A Fresnel volume, I think they call it a wave banana in deep earth tomography. This is the hypothetical area in which a wave of a given center frequency will travel through. And the advantage of that is that we have to do less interpolation. So this is an example. This is ray coverage, and the warmer the colors, the So this is ray coverage using the wave path equivalent travel time tomography method. And the warmer the colors, the more number of rays that have covered that point. So because we're using these wedge shapes to back project, we get a lot of overlap in through the area. And as opposed to if we were using infinite frequency, we would have much less ray overlap. So this was only a portion of the potential refraction tomography algorithms that are out there. And choosing the right one to use, it can be pretty difficult. Luckily, Colin Zelt in 2011 organized what we call the Refraction Tomography Shootout. And what he did was he took this hypothetical Earth model. This is supposed to be a fault with a velocity inversion, minor velocity inversion in a step, simulated a survey on it, and distributed this data to a bunch of software manufacturers. And these are all the final results. And what he found is that while some algorithms did better, all of the algorithms did really pretty much the same. Like there wasn't an algorithm that did vastly better than any of the other algorithms. And all the algorithms produced a reasonable result. So the takeaway is that you can use just about any refraction software that's currently available, and you'll get a fine result. He did note that the wave path equivalent travel time algorithm did work the best, but it was only slightly better. So what really matters when you're doing refraction processing is initial models and user inputs. So now, frequency dependent tomography. This is something that hasn't been implemented in commercial software to my knowledge. And this is where we're not making any infinite frequency assumptions. So this is an algorithm that was developed by Chen and the same Colin Zelt from the last slide. If you want to know the cutting edge of refraction topography, Colin Zelt's usually got his name on it. So these two figures here are a comparison of frequency dependent results and infinite frequency results using that same model that we use for the shootout. And we can see that frequency dependent is an improvement. We're able to more resolve this hypothetical fault here. This velocity inversion is a little bit more clear, but it's not a massive improvement. The nice thing about it is with frequency dependent tomography, it's no more processing time and effort than infinite frequency. So you get a marginal improvement for no extra processing time. Now, the last thing we're going to talk about is full waveform inversion for seismic refraction. Like I mentioned, this usually uses a clipped portion of the wavelet and incorporates the wave shape to update the model. This increases resolution by quite a bit. However, it is very sensitive to noise in the initial model. And why it's sensitive to noise is pretty easy to understand. If you have vehicle noise that's distorting your wavelet, the algorithm can't detect which part of the wavelet is from vehicle noise or from the ground. So you're going to end up with an unusual ground model. Full waveform inversion is used quite a bit in oil and gas because they have lower noise environments. So here we're showing the results, again, using the same Earth model from the shootout. This is also one of Colin Zelt's papers, where we can see the model from full waveform inversion. And we can see that it really does a great job of resolving this fault feature, this step, and this velocity inversion. And the difference between these three models is different initial models. So using an infinite frequency or frequency dependent initial model. And no matter what, it does do, no matter the initial model, as long as it reaches a certain threshold of quality, it does do a really good job of resolving the actual velocity structure. Given that there's so much benefit to using full waveform inversion, you might be asking why it's not used in commercial software. The big thing is that noise issue. I've probably done 100 seismic refraction surveys at this point, and I would guess that 20 of them had data good enough for full waveform inversion. And of those 20, I don't think the client would have really benefited from the extra effort it would have taken me to do a full waveform inversion. They are mostly interested in what is the depth of bedrock or what is the fault. They don't care that if I can make a pretty picture. They would like it if I could, but they're not willing to necessarily pay the extra 2 or 3 days of processing effort it would take for me to do that. So in summary, refraction methods are used a lot for structural characterization because they have good lateral resolution. You cannot image below a laterally continuous velocity inversion in most cases, but you can say something about a velocity inversion if you're able to put the array half on the inversion and half off. You should choose an initial model carefully. That's probably the thing that's going to affect your results the most. And I always recommend trying more than one and try to do the inversion with more than one set of inversion parameters. And this leads into always be aware of non-uniqueness, always be trying to vary your model to get a bunch of different potential outcomes, and then use as much a priori information as you can to choose which model is going to be the best. And while there are multiple methods implemented, or multiple refraction processing methods implemented in commercial software, they all work generally well. It's mostly up to the user to determine the quality of the result. And while it's not necessarily in commercial software yet, I do think there is room for frequency-dependent travel time tomography to be implemented in commercial software in the near future. The algorithm is published in an easily accessible journal, so it just takes someone who is motivated to write up the program. And while full waveform inversion will produce the best results, because of the burden of very clean data and extra processing time, I don't think it will replace travel time tomography. I do think it will become more commonplace because there are situations where it does make sense to do it. Some resources I would like to share that I find very useful is Refract. This is the commercial software that we use. The owner has done a great job collecting all of these resources on, or all of these academic resources and papers and case studies on the implementation of refraction methods. And in particular, the thesis by Stefan Johnson really does a great job overviewing the state of refraction tomography. And with that, I'll start answering some questions.
Okay, so the first question we have is there a particular way to hit the plate?
Yeah, so there is a better way. So in an ideal world, you'd hit the plate once and hard and you wouldn't have any bounce. That being said, because if you bounce the, say you bounce the hammer, the waves associated with that second hit are going to be offset in time from your first hit. So if you've got a little bit of bounce, that's fine. And the reason why we try not to bounce the hammer is oftentimes when we do refraction surveys, we're also doing MASW surveys. So if your goal is to use your seismic data set for both, you want to hit the hammer as vertically as possible with one clean hit. After the hit, you try to catch the hammer. There are other things that are helpful, like at Olson Engineering, we make these custom plastic backed aluminum plates. The plastic really helps with the coupling with the ground, and also helps with bounce. And since it's aluminum, it's a little bit lighter. Okay.
Okay, second question is, what about use in karst terrain?
Yeah, so karst terrain, you can use seismic refraction in karst terrain. You do have to be aware that if you had like a hypothetical laterally continuous karst, you're going to have issues with that. If you've got more discrete karsts that are smaller than your array, then seismic refraction will work fine. This is again a situation where we would recommend using seismic refraction in conjunction with MASW.
Next question is, would you use S-wave refraction if you know you have water table above the top of bedrock?
Yeah, you could use S-wave refraction if you know you have a water table above the top of bedrock. This is a situation where I would recommend MASW over refraction tomography. And I can't remember where I was going with that. If you're in a weathering environment, so if you're in a low porosity environment like the weathering zone, you're not necessarily even going to see the water table with a P-wave refraction survey. The water table is only an issue with a P-wave refraction survey in an alluvial environment. And if the water table and the bedrock are not that far apart, you're going to get refractions from both of them, so you'll be able to image both of them.
Okay. Is there a topography limitation for this method? For example, can you apply it only in flat ground, or can you use it in sloped terrain? If so, what is the maximum slope permitted?
So you can use it in undulating and sloped terrain. The only thing that you need to be aware of is you need to have a receiver density high enough that you're actually characterizing the shape of the slope. And as far as a maximum slope permitted, as long as you can stand on it and put a geophone in, you should be fine. The big thing is if you're in a situation where you've got a bunch of hummocky hills, you can't have one receiver at the top of the hill of each hill. Then you're going to get some weird results. So you want to have a receiver density enough that you're characterizing the slopes of your surface.
Okay. Next question is, does it give the density conditions in the fill?
Not directly. So you can you can say that velocity increases with density. So you can say a relative relationship. So this area has a higher velocity, so it's more dense. There is no easy equation that goes from P wave to density directly.
How do you estimate the RMS error?
So the RMS error, that is, I don't remember the equation itself, but it is the error between the simulated first arrival and your picked first arrival from the survey itself.
If you know there is a low velocity layer in your survey area, then how will you create or make your initial model?
So one thing I didn't mention, because it's a little bit more of a sophisticated way to go about this, is if you constrain your high velocity layer, so you can actually do refraction tomography. So if you know how thick your high velocity layers, you can do that. That being said, if I knew I had a low velocity layer, I would create my initial model. The process of creating it is somewhat tedious, but I would try to replicate how I think the actual structure is. So assuming that I had some boring information, I would create a top layer that was 5 meters thick, that was X velocity, and then I would use a middle layer that was 10 meters thick of X velocity. And So I would try to create an initial model like that. I wouldn't necessarily want to use one of the computer-based methods in that situation. Generally, though, if I know that there's going to be a velocity inversion, I'll just use MASW.
Okay. What's your favorite software to use for processing at Olson Engineering?
So for 2D refraction, we use Refract, and this is the one that uses the wave path econal travel time method. And I don't like it just because it uses that method. I find that it gives you a lot of options for choosing your initial model. And like I said, initial model is probably the most important thing. So that software, because of its ease of generating initial models, is generally my favorite. Like all seismic software, or like all geophysical software, it's not easy to learn how to use, but it's not impossible. And it's actually it's stable. It doesn't crash very often, which I like. And it outputs directly into Surfer, which I also really like.
Okay. For generation of tomographic inversion model, how many shot points are required for a 24 geophone spread?
That's going to depend on what your resolution is. So for a 24 geophone spread, I would do a shot location at every third geophone generally. I tend to err on gathering too many shots than too few, especially if I only have 24 geophones. The time it takes to collect extra shots is much less than the time it takes to lay out the array. So I try to. So if I'm really, really interested in trying to get lateral resolution, I only have 24 geophones. I would do every third geophone as my shot location.
Okay. What is the size of your 2D grid for the tomography?
It depends on the model. Usually it's some fraction of your receiver spacing. And I'm assuming you're talking about the output, what I actually output to Surfer. Yeah, that really just depends on the survey itself. There's no straightforward answer.
Okay. It appears that no one is considering anisotropic media. Is that true?
So in academia, there has been quite a bit of work on measuring anisotropy with seismic refraction. And what you do there is, rather than having one survey, you create a wagon wheel survey. So you're doing a bunch of lines that are offset by a certain degree. And from that, you're able to actually estimate a degree of anisotropy. If you go to the Refract website and look for a thesis by Aida Mendieta, she did this at Boise State, where I went. She's got a really good thesis on how you deal with anisotropy and seismic refraction. And this is particularly in a weathering zone in Idaho.
Okay, this might be very similar to the other question that was asked, but what would your suggestion for best commercial software for data processing of refraction data be?
I really like Refract. One limitation I didn't mention about Refract is it doesn't do 3D surveys. Rarely do I feel like it's necessary to do a true 3D survey rather than a series of crossing lines. But GeoGiga does 3D surveys, and it works pretty well.
Okay. Is there any case where a comparison between downhole method with refraction method, which one is more precise?
So you're able to gather more information with a downhole method. But depends on what you're asking. If we're talking about, because you can do refraction surveys where you have a string of geophones or hydrophones down a well. That is an ideal situation, especially if, like, say you're trying to image the extent of a karst. So if you just have a surface spread, then you have a limited number of ray pass. If you had a surface spread and then a borehole, then you have ray pass going from the surface to the borehole. That case is that's the ideal case. if you're talking about doing a sonic log velocity, your sonic log velocity is going to be more accurate. But when an interesting fact is if you do your refraction tomography right, when you do a spatial smooth of your sonic log, it should look like the 1D velocity from your velocity model that you did with refraction.
Okay. Do you have some successful case studies related to concrete near-surface damage evaluation?
Not with seismic refraction. The issue that you run into with seismic refraction on concrete is that because the waves are traveling so fast at 12,000, 14,000 feet per second, you're not getting good distinction between your P wave arrivals and your refracted P wave arrivals or your surface waves. It all just kind of blends together. And the other issue is that you'll run into is I don't think the geometrics geode could sample fast enough to really do that. If you're talking about concrete surface damage, we would recommend something called an impact echo method or impact echo scanner, which is something that we develop in-house. It uses a very different processing method, but it is very good at evaluating concrete damage.
Okay. Please discuss ray path coverage plots, resolving small lateral variations as from core stones, and causes of waveform inverting from one geophone to another.
Okay, so let's go back to the coverage plot because I didn't explain that super well. So the coverage plot is, in this case, this is the back projection envelope from each shot and receiver pair. So for each shot, you're modeling a ray to every one of the geophones. And then you're back projecting along that Fresnel volume. So the more coverage or overlap you have between Fresnel volumes, the better constrained your model is going to be. That's why, but that being said, because the Fresnel volume in the software is user defined, so it's based off of you choose a center frequency for your refracted arrival. If you choose it to be too wide, what will end up happening is you'll smooth your model out artificially, as opposed to if you choose it too narrow, you can start to introduce artifacts. Okay, so question 2, resolving small lateral variation from core stones. At depth, your core stone is going to need to be pretty big. At the surface, you might see a core stone that's like, say your receiver spacing is 5 feet. If you had a like a 10-foot diameter core stone, you'd probably see that in the data. In fact, I have a good data set that I didn't add into this that would show that. So it just depends on where the core stone is. It's not, if you're trying to define the location of a core stone, refraction tomography is not what I would use, because I'm assuming the core stone is going to be near the surface, so I'd probably use GPR. Causes of waveform inverting from one geophone to another. Usually that's because you plugged in the geophone backwards. That, I think, is the only common time I've seen the waveform inverting. Are you able to use refraction / MASW for determining?
For demining.
Oh, for demining. What do you mean by demining? We'll get back to that one. I know about GPR for actual mines, but we're finding aerial ball. Oh, demining, not for UXO. No, I wouldn't use MASW refraction for UXO. It's because of resolution limits. You would need a pretty big bomb, like bigger than I think any bomb's ever been made. That being said, I know GPR is one method for it, like you mentioned. I would actually say finite frequency domain electromagnetics is probably going to be a great way to do that. I think that's what the EM61 is pretty much designed for. Okay.
Okay, the next one seems to be more of a comment than a question, but he says that I'd say that ultrasonic pulse refraction works pretty well in case of fire damaged concrete cover.
Yeah, I could see that working. I haven't spent too much time trying to do refraction on concrete, but what I have seen is it is kind of difficult to resolve what is the refractor. That being said, ultrasonic pulse methods are pretty slow and labor intensive. That's why we tend to use impact echo scanning. We can scan at that speed with impact echo. Rather than ultrasonic pulse, you have to put your sensors on in some way, pulse, 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 re-grease it, put in a new location, pulse, pulse, pulse again. But if you wanted to do something a little bit more tomographic, that would be a pretty good result. Like if you had a column and you wanted to do ray pass through the column, then yeah, UPV would be great.
Okay, next question is, non-tomographical methods generate 2D model artifacts. How will you decide these are due to artifacts or anomaly due to some feature?
There's a lot of ways. So we look at so when I say artifact, it's something that's obviously weird. And obviously and we rarely approach a situation where we don't have a priori information. So whenever I'm evaluating any model, whether it be the non-tomographic methods or the tomographic methods, I'm always trying to see, like, does this velocity model actually make sense? Does it make sense that we have this giant velocity anomaly here? Does that giant dip in bedrock topography actually reflect what we expect to see? So I guess I'm not really answering your question, but I'm saying to decide what is an artifact and what isn't an artifact, you have to bring in other information, and you will oftentimes try to compare other methods. So if you have an artifact that you're really on the fence on, then I would try to process the data for MASW, just so I can see what that one looks like.
Okay, next question is, please discuss off-end shot locations and refract requirements.
So off-end shot locations, you can get yourself into trouble with if you do off-end shot locations. And I want to bring up, it's way back here. Okay. So where I have drawn this shot location is actually not where I would actually want to choose an off-end shot location. Say I have a fixed array where I'm not moving it. If I shoot, like my first method, or when I do a fixed array survey, I don't do shots more than a foot away from the first or last geophone. The reason why I do that is, say my shot is over here, I'm modeling arrays that are traveling from over here to over here, but I can't say I have no constraint over the velocity over in this area. So I'm introducing a lot of potential unconstrained data. If I'm doing a roll along survey, so I would shoot near the first geophone, between the third and fourth geophone, between these two strings, and I would actually continue on a little bit. I wouldn't go all the way into the second spread, but I would continue through a little bit. And then after I roll the spread over here, I'll actually start shooting. I'd actually repeat some of the shots that I had done through the previous spread. And the reason why you can do this, and these will look like off-end shots, which I just said don't do, but the reason why you can do this, you can repeat these shots, is because we're doing shots with geophones at these locations, we have some information about the velocity structure in this area, so we can more properly model the arrays. Refract requirements. So refract takes seg D I think it's seg D and seg Y. Beyond that, it doesn't really require anything special. It doesn't do great GPS integration. Yeah, it runs on standard PCs. If you have any other more specific questions, you can ask them.
We just had a question related to what you were saying. It says, but the off-end shots can help with the initial model, no?
Again, if you don't have geophones in that area, you can get into trouble because you can't properly model the first half of your ray path. So I would still hesitate to do too many off-end shots. I mean, you can collect off-end shots and not use them in your processing. We'll often do that. Like when I say I don't do off-end shots for seismic refraction, because most of the time we're combining seismic refraction and MASW, and MASW, because it's geophone to geophone comparison, we'll collect those off-end shots anyway.
Okay, we're gonna get back to the main line of questions. How many shots do you typically do across a single setup? Do you tend to increase the number of shots with usually undulating topography?
So number of shots per specific setup. So if I have a 24 channel system, I would do 6 to 12 shots, I would say. I don't really want to go beyond that because it just takes too much time. It takes more time. And I'll just vary that based off of time available and resolution requirements. I will increase the number of shots if I have undulating topography.
Okay, next question. How does impact echo scanning compare to REMI surface line over concrete?
So impact echo is going to image, so when you're talking about REMI over concrete, are you saying you're interested in the concrete itself or what's below the concrete? Because impact echo won't tell you anything below the concrete. And I'm not familiar with anybody doing REMI to look at concrete. So if you could clarify that, we'll get to that question.
Okay. Is there a way to determine if the results are showing a potential void, i.e. fluid-filled mine or rock? Is there a high conductivity noted?
So you're asking if I have a void, can you tell if it's full of liquid or air? And the answer is usually yes, but it depends on the material. So in order to see something, we need to have a velocity contrast. If your saturated rock has a similar velocity to water, then you're probably not going to see that. Yeah, so it depends.
Okay. Next question. For mapping deeper karst features, can we use refraction microtremor instead of refraction tomography?
I'm not a REMI expert, but I would assume that you can. The issue that you're going to run into is REMI doesn't have great lateral resolution, so you're going to have a pretty big void. And if you're interested in karsts near the surface, so in the upper 50 feet, refraction tomography is going to resolve that better.
Okay, next question. Have you had any experience with dampening of hammer blow to plate in wet superficial soils?
Yeah, so we've had issues where our plate has sunk into the ground in overwatered lawns, super damp soils. And actually, once your plate sinks into the ground, and if it's stable and not sinking anymore, you get great coupling. So you actually get better energy input from your hammer strike. So as I would say, you're going to be fine as long as your soils are not super saturated, when you're going to have probably some weird yeah. And as long as you're not losing your plate, I think you'll be fine.
Okay, this looks like to be the last question. What are the best resources you have found for soil and rock strength correlations to seismic velocities?
It depends on well, okay, rock strength. There's not really a great resource for that, unfortunately, because the relationship between rock strength and P-wave velocity is so multi-parametered and non-linear. It's really hard to establish good relationships between the two. That being said, shear wave velocity tends to be a little bit more interesting for soil and rock strength than P-wave velocity. So you might want to do a shear wave survey or a P-wave survey. And these things will vary usually. These things will vary usually in conjunction with each other. So higher velocity, higher strength, but that's not always going to be universally the case. We got one more. Can you talk about the velocity paragraph, i.e. or paradox, i.e. velocity inversely related to density? I cannot. I actually don't know much about that. I'm sorry. I wish I could answer your question. I can look into it and email you if anything I find, though. If you have any other questions, feel free to email me. Thank you for attending. This had great turnout. This is being recorded, and we will post the video to YouTube, and we can send a link to everybody. And it will also be available on our LinkedIn.